let's do this. This is for the first few chapters of your introductory chemistry course. Typically, depending on how you start, it could start off with a lot of physics stuff. So I'm going to go over the main physics points in the introductory chemistry course, along with scientific notation and units, just to kind of get you up to speed. Some of this stuff is a little tricky, and I don't think the chemists really cover it correctly, but I'm going to do it the way they do it anyway. So let's start off with scientific notation. I have another video that goes over this in more detail, so I'm just going to say this really easily. The first thing is, let's say I have some distance x equals 1,000 meters. It's not a big deal to write 1,000 meters just as 1,000, but it's possible I could actually write this as, or let's say this is, let's say I have x is 2,000 meters. Well, it turns out that you can also write this as 2 times 10 to the third meters, right? Because 10 to the third this is equal to 2 times 10 to the third is 10 with a 1 with 3 zeros, and then it still has the units of meters. And then I get 2 times 1,000 is 2,000, so I get the same thing. I'm not sure how much I really want to go into this. I will show you one quick thing on the calculator, though. But the other one is, let's say I have something like a wavelength equals 3 nanometers, and I'll do unit conversion in just a second, and that's 3 times 10 to the negative 9th meters. So this is important because no one wants to write out this, which would be equal to 0.1, that's 1, 2, 3, 4, 5, 6, 7, 8, 9 meters. No one wants to write it like that. That's just no fun. So let's do this, though. Let's multiply two numbers that have scientific notation, because there is something that you can do. You can do it in your calculator, but let's say I have 2 times 10 to the third times 3 times 10 to the negative fifth. So these are actually just numbers, and in multiplication, the order of operation doesn't matter. So I actually can multiply 2 times 3 and get 6, and then multiply 10 times negative 10 to the third times 10 to the negative fifth. So this would be 10 to 10 to the third times 10 to the negative fifth. And those are times. But if I multiply 10 to the third and 10 to the negative fifth, I can just add their exponents. So this is going to be 6 times 10 to the negative 2, because 3 plus negative 5 is negative 2. So that's an easier way to write it. So finally, on your calculator, I do want to encourage you to be very careful. If I do this on my calculator, you should learn your scientific notation buttons on your calculator. So you can write this as 2 times 10, and then, where's my hat? 3. Okay, you can write it like that. But you can get yourself into trouble if you do that. If you're going to use this method, it makes more sense to you, put parentheses around that. So actually do it like this. 2 times 10 to the third, close parentheses, because then it'll treat that as one number. The problem comes when you're dividing by scientific notation stuff. Now, the other way to do it is to say 2 and then use this EE button for scientific notation and then press the 3, and that's the same thing. You see, you get the same thing. So I would encourage you to practice using the EE button for scientific notation. One thing is, if you want to do 10 to the fourth, and you want to do that in scientific notation on your calculator, don't do this. Don't do 10E4, because that's 10 times 10 to the fourth. You don't want to do 1E4, right? Because the 10 to the fourth is already there. Okay, that's scientific notation. Let's go to units. Yes, I am going fast. So if I measure stuff, then we have to have units. So some of the most common units, the base units that we're going to have are, we have distance in meters, time in seconds, mass in kilograms, kilograms. And pretty much everything is composed of these 3 units in different ways. But for instance, energy, which we'll talk about in just a second, is in joules, which is 1 joule is equal to 1 kilogram meter squared per second squared. And this is important because if we're dealing with things in energy and joules, it tells us that my quantities have to be in kilograms, meters, and seconds. There are other units for energy. There's a calorie, which is 4. Was it 4 point? What was it? It's 4. I don't use that. 4.184 joules. Then there is the calorie with a capital C, and that's 1,000 calories, and that's equal to 4184 joules. So this is the chemistry calorie, and this is the calorie of food. When you look at food, they're listed calories and it's 1,000. I don't know what brilliant person decided to make this thing. They're both called calories, but that's that. There's also another unit for energy, the electron volt. 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. That's important. Okay, so let's just talk about unit conversions. I want to convert, let's say I have a distance of x equals 1 centimeter, and I want to convert that to meters. So the key here is if I multiply this by 2 over 2, then I can do that because I have to multiply both sides. This is an equation. I have to multiply both sides of the equation by 2 over 2, but 2 over 2 is 1. So I'm not changing anything. I don't actually have to multiply this by 1. So this is fine. So as long as I multiply by a fraction of 1, I'm not changing it. So what if I did this? X equals 1 centimeter, and I multiply that by 1 meter over 100 centimeters. 100 centimeters is 1 meter, so I'm multiplying by 1. But this unit of centimeters now cancels, so I have 1 times 1 is 1 divided by 100, so I get 0.01 meters. That's how you do the unit conversion. Multiply by 1. I guess I should really quickly remind you about some of the prefixes that we have. You're going to see a bunch of these prefixes like milli. Let's see. Let's just do all these in meters. 1 millimeter is equal to 10 to the negative third meters. 1 centimeter is 10 to the negative 2 meters. 1 kilometer, I'm going to write it out, is equal to 10 to the third, 10 to the third meter. So milli means 10 to the negative third, centa is 10 to the negative 2, kilo is 10 to the third. And it doesn't matter if it's kilograms or whatever. So those are the ones you'll see for normal size objects. There's another one like mega. 1 megameter, that's a capital M, is 10 to the 6 meters. What else do we have? A nanometer. 1 nanometer, lowercase n, meter is 10 to the negative 9th meters. You should probably memorize these. Sometimes they will give you these conversions, but sometimes they'll expect you to know them. So it just depends. 1 picometer, PM, is 10 to the negative 12 meters. Then there's an angstrom. 1 angstrom, it's equal to 10 to the negative 10 meters. That comes up in chemistry a lot too. So these are some of the conversions that you should probably remember, and you can use those to convert things. Let's do a quick example for. I'm going to just do one example. I think I have another video on unit conversions. So let's say I have something like this. Area is 10 square centimeters, and I want to convert that to meters squared. Well, in this case, if I multiply this by 1 meter divided by 100 centimeters, then this is the number 1. But it doesn't cancel because I have centimeters squared divided by centimeters. So it wouldn't work. So what I actually need to do is to do this twice, right? I need to multiply by 1 meter again divided by 100 centimeters. And now these two cancel with that, and I get meters times meters, so I get meters squared. So it's going to be 10 divided by 100 times 100. So this is 10, and that's 10 to the negative, that's 10 to the fourth. So I get 10 divided by 10 to the fourth, and that's going to be 10 to the negative third meters squared. So you can do that. You can have multiple things in the line, but I don't want to talk about that too much because we got a lot of other stuff to do. Okay, so that's units. Let's talk about energy and power. So energy is a way we can count stuff essentially in real life that turns out to work all the time. It's nothing. It's something that we made up that works, and it comes from this. Work is a change in energy. This is the work energy theorem. It says if I do work on some system, then that system has to change energy. I'm not going to go into work and things like that, but that's the basics of it. And depending on how we choose our system, we can have different types of energy. So one of the common energies that you'll see is kinetic energy. This is the energy associated with an object that's moving. So for a moving object, we have this 1/2 the mass of the object times the velocity squared. And again, if the mass is in kilograms and the velocity is in meters per second, then this will be in units of joules. And that's what you usually want. Another common unit, you may not see this, is like something like gravitational potential energy, mgy, where g is the gravitational field. I don't think that you'll deal with that too much. But another one is the Coulomb potential. I'll call it UC, and that's K times Q1, Q2 over R. So if I have two charges, Q1 and Q2, separated by a distance of R, then that's the potential energy associated with the system. And so here, K is the Coulomb constant. So let me start a page. Let me start a little note with constants, and then I'll make sure we have these. So K is equal to 9 times 10 to the 9th Newton meters squared per Coulomb squared. So that's, and again, I don't know if you're going to need to memorize those or they give them to you. I guess I should go ahead and say if these are an electron and a proton, electron, they have a fundamental charge of E equals 1.6 times 10 to the negative 19th coulombs. So there's another constant. Okay, another type of energy. I'm trying to think. I mean, technically there is this. There's this. You'll see this at some point when you talk about nuclear stuff. E equals mc squared. And this is the energy, the mass to energy relationship, where c is the speed of light, another constant. C equals 3.00 times 10 to the 8th meters per second. That's how fast light goes. Let's see. Is there another? Okay, it's not energy, but we also have momentum. And this is going to come up later, where momentum is lowercase p is mass times velocity. And that's a simple way to write it. It's actually more complicated than that, but and this is simple too. And so the important thing is that there is a relationship between this and kinetic energy. So if I square both sides of that, I get p squared equals m squared times v squared. And then if I divide that by 2m, I get 1/2. One of those masses cancel, and then the velocity is there. So, that got to divide that by 2m too. I do both sides. So that is kinetic energy. So I get K equals p squared over 2m. So there are things when you need the momentum instead of the kinetic energy. So there's that relationship. Okay, one last thing for energy, and I think I'll make sure I'm on the page, and that's power. Power, we use capital P, and it's the change in energy per time. It's how fast you either take or give energy. So if this is in joules and that's in seconds, then this would be in units of watts. So 1 watt is equal to 1 joule per second. Another common unit of energy is horsepower, but I don't think that you'll see that. You may see something like kilowatts. A kilowatt is just 1,000 watts. Okay, again, going back to that prefixing. Okay, that's energy. Let's talk about the Bohr model of the atom. So when they started looking at the properties of matter, they came up with this idea, and I don't want to go through the whole thing, but if you take hydrogen, you could represent it as a proton right there with an electron moving around a circle some distance r away. And that's the Bohr model. So it says an atom is like a mini solar system. Just like the Earth orbits the sun, the electron orbits the proton. Now, this is a wrong model, okay? But this says that there is a electric force pulling on the electron, just like there's a gravitational force pulling on the Earth. And if this is moving with some velocity v, then it orbits. It's wrong, okay? But it does, in fact, work fairly well. But one of the things that they found was if they say that, what did they say? They said if lambda, I'm going to write this out. If you assume that an electron has a wavelength, then I could draw this like this. It's kind of hard to draw. If that wavelength depends on two things, Planck's constant, h, and the momentum, there you see with the momentum, then you can only have an orbit if this has a complete number of wavelengths on there. And I'm going to talk about wavelengths in just a second. But let's go ahead and write down Planck's constant. H equals 6.626 times 10 to the negative 34th joule seconds. Okay, there's Planck's constant. So if you increase the orbital distance, then at some point you get to another electron wavelength and it does have a stable orbit. But the end of the story is that you only have certain energy levels that are allowed. So I can have, for hydrogen, I have En equals negative 13.6 electron volts divided by N squared. So N can be equal to 1, 2, 3, 4, and so forth. But it can't be 1.5. It can't be anywhere to. It can be here or it can be there. It can't be in between. And this is the quantum nature of matter. It's super important. It means that systems can only have certain energy levels. If you change this to helium, helium looks like this. There's a proton, there's a neutron, there's another proton, and there's another neutron. So instead of a single proton in the nucleus, we have 4 particles, but the neutrons are neutral. And if I have an ionized helium, so there's only one electron, then it has energy levels that look like this. It's just negative 4 times 13.6 electron volts over N squared. Okay, and then this is in electron volts as a unit of energy. And that's important because then you can find, if you want to look at the change in energy, delta E from 1 to 2, it would just be negative 13.6 electron volts times the final energy of 1 over 2 squared minus 1 over 1 squared. And you can get the change in energy. Okay. Look at my notes here. Okay, that's good. So let's talk about, we talked about the Broglie wavelength. Let's talk about light, because light is also a wave. So if I imagine a wave like this, it has several properties, and this is actually electric field. We'll talk about that. The first is the wavelength. It's the distance from one peak to the next peak, and we use the Greek letter lambda to represent that. We could also imagine sitting right here and having this wave go past us, and it goes up and down, up and down, and up and down. And if you look at how many times the wave passes this point every second, that's the frequency. So this is the wavelength. And that has units of meters. And then I have the frequency. A lot of times they use the Greek letter nu. It's not a V, it's a nu. And that would be the frequency. And it's how many times per second. So it'd be in units of 1 over seconds. We call that also a hertz. So the other common symbol is F. And then the last property of this is the speed, how fast if you looked at one piece of this and just said it's moving, that would be the speed. Now for light, this is an electromagnetic wave. So that means it's actually an oscillation of electric and magnetic, which we use B for, electric and magnetic fields. So, and we're not talking about waves, we're not getting into that, just as long as you know that it is a wave of electric and magnetic fields. But one of the properties of light is that it always travels at the same speed. So we have this relationship, C equals lambda times the frequency. Very important. Where C is the speed of light, I've already given you that. So if you have wavelength times frequency, you do get speed. Now, let's talk about the photoelectric effect. Because this was an early experiment that kind of said, hey, maybe light's more complicated than that. And in fact, it's complicated, but it has to do with this photoelectric effect. And I feel bad saying this, honestly, because I don't agree. And photons. So this idea of photons is super common in chemistry. It's not really the best model, but it's still used, so I'm going to explain it. And the idea is this: if I have some metal and it has positive and negative charges in there, it turns out that I can get these negative electrons to be ejected by shining light on it. There's my light. And there is energy in the light, and it turns out the following is true. The energy of the light is equal to K plus phi. So this is the energy of the light. This is the kinetic energy of the electron. Remember, that's electron. That's 1/2 mv squared. And then this is the work function. This is how much energy you need to break that electron out of the metal. And it turns out that by changing the frequency of light, by increasing the frequency of light, we can get more energy of these electrons. So from this, you get the energy of a photon is h nu. That's the energy of one single photon. And it says, okay, it's as though light is a particle. It's not actually, but it's as though that is. And the higher the frequency, the greater the energy of that. Now, if I use this up here, I can solve for nu equals C over lambda. And if I put that in up here, I get this is also equal to hc over lambda. So you have two ways to calculate the energy of a photon: the frequency times Planck's constant, or the speed of light times Planck's constant divided by the wavelength. But they're all the same thing. Okay. And a lot of times this work function will be given in units of electron volts. So if you want to use the kinetic energy in terms of velocity, then you have to convert from electron volts to joules. Okay. If when in doubt, convert everything into joules. That's going to work out better. Make sure the mass of the electron is in kilograms too. There's another one. The mass of an electron, 9.11 times 10 to the negative 31 kilograms. Okay, where are we at now? Power unit, de Broglie wavelength. I think I got everything. Yeah, I think I got all the really big ideas. I mean, there's a lot of problems, and they can make it more complicated than they have to. But that is, I've had a list somewhere else. Did I get through my list? Where did I put my list? Okay, well, I think that's good. Other constants. Did I get other constants? That's moles, right? 1 mole is equal to 6. What is it? It's 6.022 times 10 to the 23rd. It's a number, right? If I said 1 dozen equals 12, 1 mole is that. So that's something that comes up a lot, especially in chemistry, because this is a macroscopic way of determining things. Whenever you think of mole, just think it's a number. It's just a number of particles. Okay. I think that's good. A good start. You may do things in there like temperature and energy, but I'm not going to talk about that right now. I think that's enough to get you started, and hopefully they find that helpful. If not, it's not my fault. I'll include a link to scientific notation and unit conversions down below. Hopefully those will help you too.